Swayam Prabha. Digital India. Educated India.
To do that, what we do is, first of all, and we are not very far away from the end of this class today. I do not want to introduce too many concepts in the same day, especially as we have another class tomorrow. Tomorrow we have a class at 5:45 p.m. same place, right. First of all, let us introduce the concept of function space, and let us go back to that refrain, please do not get scared. Function space is no rocket science, it is not very difficult to understand it at our level, it is fine. So, what we mean by function space is just a collection of functions, let us put it that way. Do not think of it as space where you can sit down and have your biscuit and all, collection of functions, okay, f1, f2, f3, etc., so on and so forth, okay. And an example of function space is a collection of, say, the position vectors, p1, p2, where is p3, p3, p4, are the colors showing up? I do not see them very well. Achha. And what we have done is we have drawn these position vectors in 3-dimensional space x, y, z, and the unit vectors, the base vectors are e1, e2, e3 as usual. Right handed Cartesian system, is that right? Is it a right handed axis system or not, the way I have drawn it? X, y, z, right handed or left handed? The days of left handedness are over, better be right handed, okay. Even position vector is an example, position vectors are examples of functions. So, see, position vector is something that is easy to understand, right, because it is in tangible space. So, I have used them as an example, that is all, okay. These are examples, this is not the general picture. So, it is a collection of functions. Now, they have to satisfy certain properties, then only can you call that collection function space. What are the properties? First of all, fi plus fj equal to fk, you add up any two functions, you get another function in the sense another function in the same collection. Now, think of any two position vectors, say p2 and p352, add them up, what do you get? Vector addition, you get another vector. Where will the origin of that vector be? At the origin, I am talking origin, where will it begin? Origin of vector will still be 0, 0, 0, right. So, that vector will also be a function, that vector will also be a position vector, right. So, this is satisfied by position vectors, fi plus fj equal to fk, got it, fine. What are we trying to do here? We are going to define something that is completely abstract, a function space, can be anything, right. Then we are going to define an operator. By now everybody is familiar with the use of operators on vectors, right, eigenvalue equation and so on and so forth. So, that is the approach we are going to take. We are going to make an operator operate on these functions and then see what comes out, and what will come out is going to be a perfectly general picture which we can use for any system that we want, right. So, the thing is, we started with symmetry, we talked about matrices, today we came back to symmetry and we have established a little some connection between what we discussed in the first 3 classes and in the next 3 classes. Now, we are seemingly making a little bit of departure once again, but it is not really a departure. It is just that we are defining the same problem of symmetry, which is tangible, in a little more abstract term. Okay. And the reason why we need an abstract definition here is that we need generality. So, in case I lose you anywhere, please do not hesitate to stop me, and we will go back a little and come back, but it is important that we understand. Fine. Second point, NFM equal to Fn, does it work? Does it work for position vectors? It works. Just multiply by a scalar, you still get a position vector. To make things more convenient, the direction of this position vector is the same as the position vector that you started with, alright, just multiplication by a number, scalar. Okay. Third is a combination of first and second. A linear combination of the projection vectors, a linear combination of the functions is also a function. That I think you can understand easily. Take a linear combination of any number of position vectors. What you get once again is a position vector. Okay. Multiply each vector by whatever number you want, does not matter. What is the definition of position vector? Must begin at origin, can point in any direction, right, can be of any length. So, no problem, right. So, position vectors so far are falling in line with the definition of function space that we have defined. Great. Next, this is what we perhaps know. What is F1 comma Fi comma Fj in bracket? Yes. What is that called? Another word? It is a scalar product. It is a scalar product, right. So, the scalar product is defined as integral Fi star Fi d tau, integrated over all space. Okay. That sounds scary. I am scared whenever I see an integral, right. I get extremely scared when I see an integral. Printing mistake. I hope the printing mistake has not continued later on also. I hope I did not delete something. Yeah, alright. So, this is the definition. Let us see what it means. Whenever I get scared by the integral sign, I remind myself that an integral is just a summation. Then I am a little less scared. Because even my 7-year-old son can add. Okay. Addition, when you say addition, it is not all that scary. When you say integration, at least I get scared, right. So, let us see, let us take an example once again of two position vectors, and let us see what the scalar product means, and let us as we will see, it will turn out to be an addition of the same form. Okay. Pi Pj. So, printing mistake has not continued. Pi Pj equal to Pi Pj cos theta, right. J is just a subscript, Pj means jth P, not the usual meaning. This is a Pj. Pi Pj equal to Pi Pj cos theta, right. So, let us work this out for the position vectors. To help you, I will write this: Pi equal to xi E1 plus yi E2 plus zi E3, and Pj is equal to xj E1 plus yj E2 plus zj E3. E1, E2, E3 are the base vectors, unit vectors along x, y and z directions respectively. Now, if you take the product, what do you get? Xi, xj, E1, E1. What is the dot product of E1 and E1? 1. What is the next term? Xi, E1, yj, E2. So, xi, y1, E1, E2. What is that dot product? 0, right. Cos theta is 90, right. So, this is what you get, very simple: xi xj plus yi yj plus zi zj. Okay. So that is somewhat like a sum. Well, that is a sum. That is a sum of products. This is also a sum of products, right? Fine. Next one is a little unusual in this course. Generally we do not have paragraphs, we only have bullet points. This is a paragraph, and what we are saying here is something that you know very well. It is just that I have said it in many words. If n of the functions are linearly independent, what is the meaning of linearly independent? What is the meaning of linear independence? Yes, yes, go ahead. Exactly. You cannot write any vector, any of the linearly independent vectors as a combination of the other ones. So, the formal definition is this: linear independence means sum over I ai fi has to sum over I ai fi equal to 0 if and only if sum over I ai is equal to 0. No, all these are 0. A1, A2, A3, A4, everything is 0. This second sum is not right. If all the AI's are 0, that is a trivial solution. Otherwise, you cannot write sum over I AI fi equal to 0. Let us take the easiest example that we understand. Take x, y and z. Can you write something into x plus something into y plus something into z equal to 0? Can you write? How? Something into x plus something into y plus something into z. Do not forget what it means. Something into x plus something into y plus something into z is a position vector, right? When will the position vector be 0? When the coefficient of x is 0, coefficient of y is 0, coefficient of z is 0, right? Trivial solution. Otherwise, the point is this: you have x, y and z, take x and y. Okay. If they have a non-zero resultant, it will be in the xy plane, right? That means what? It will be perpendicular to z axis, right? So, vector sum of something in xy plane and something along z can never be equal to 0. Is that right? Something in the xy plane and a vector in the xy plane and a vector along z, no matter what the angle is, right? This is the angle, never be equal to 0. That vector sum will never be equal to 0. Or in other words, if you transpose, that is what I think Shantanu was saying, you cannot write something like z equal to ax plus by unless everything is equal to 0. Okay, this sum is not right. That is just again. So, you understand what I mean by linear independence? So, let us go back to this definition now. If n of the functions are linearly independent, then any of the other functions can be represented as a linear combinations of these n functions. Very easy to understand once again in terms of position vectors and base vectors. Any position vector, think of any position vector, you always write it as xi e1 plus yi e2 plus zi e3, okay, the components, any position vector, right. That is basically what we are saying here. If n of the functions are linearly independent, in real space we have 3 functions that are linearly independent, right. Then any of the other functions can be represented as a linear combination of these n functions, okay. In other words, what we say is that we say that this space is n dimensional, the space here is 3 dimensional, okay. So, just because you have many vectors, many functions, suppose you have 480 functions, it does not mean that we are working with 480 dimensional space. What you have to see is that how many of these vectors are n dimensional, are linearly independent, okay. That number will give the dimensionality. How many position vectors are there? 3 position vectors only. Infinite number of position vectors are there. So, are we in infinite dimension space? No, we are only in 3-dimensional space, because 3 vectors are sufficient, right. A linear sum of these 3 vectors is sufficient to describe any position vector that you can think of. So, this is the meaning of dimensionality, not how many vectors there are, but how many of these vectors are actually linearly independent, alright, fine. And then when these are orthonormal, then this forms what is called an orthonormal basis function, right. There are many examples of orthonormal basis function. XYZ is a little boring, I have said so many times. Can you think of another example, being chemists? Think of another, let us keep it simple, think of another 3-dimensional basis function. You are chemists, do not forget, and this is a physical chemistry class, Px, Py, Pz, Px, Py, Pz, right. Now let me ask one of my favorite questions. What is the magnetic quantum number of Px orbital? Okay, people who are taking 8-1 course now do not answer. And I think it would have been discussed. People who took 8-6 last semester also do not answer. Others, and Bivab definitely do not answer. Yeah. What is the magnetic quantum number of Px? +1 or -1? What do you mean either +1 or -1? Depends on? Pz is 0, I agree. What about Px and Py? What is the magnetic quantum number? Both? You are studying 8-1. Huh? So wait, let us see if the others figure out. 103, CH 103, 107, whatever you studied, or CH 425. What is the phi part of m equal to +1 orbital wave function? What is the phi part? Theta nahi re baba, phi. Theta is theta and phi is phi, and never the twain shall meet. E to the power m equal to +1, what is the theta phi dependent part of the wave function? E raised to I phi, and for -1 e to the power minus I phi. So, is e to the power I phi along x or y? It is out of this world, it is in the imaginary axis, right. Px or Py do not have well defined magnetic quantum numbers. Okay. This is discussed in Atkins physical chemistry book among other places. The point is this, these are imaginary wave functions. Okay. If you define magnetic quantum number only when m equal to 0, what happens is you get something in cos theta. Cos theta is along z, right. What is theta? I hope you have not forgotten. This is theta, right. Starting from z, this angle is theta, can go from 0 to 180 degree. What is phi? This is phi along x phi, can go from 0 to 360, and r, of course everybody knows what r is. Now, so if this is theta, this angle, then cos theta would be along z, right. So, when m equal to 0, the e to the power I 0, what is that? E to the power I 0 is 1, right. So, that imaginary part vanishes. So, you get a real orbital, and that real orbital, since it has something in cos theta, it is aligned with z axis, that is why it is called Pz. So, for Pz m equal to 0, right. But for m equal to plus 1 or m equal to minus 1, you cannot draw them along px or py. So what you can do is you can take linear combinations, right? You add ones and subtract ones, and in one case divide by I, then you get functions that are along x and along y. Just read it from Atkins' book this evening, right? So m is not even defined. So the reason why I invoke all this is this, that m equal to plus 1, m equal to 0, m equal to minus 1, right? They form an orthonormal basis set, and px, py, pz, they form another orthonormal basis. Understand? And are these two bases completely divorced from each other? No, they even have a common member in this case, but you can generate these real wave functions by taking linear combinations, appropriate linear combinations of the imaginary wave functions. So basis can be interconverted. Transformation of basis is not impossible, it is doable, it is done, right. So this is the meaning of orthonormal basis function, right. Okay. Second last slide. So now I hope we have at least some idea of what basis functions are, right, what a function space is. So we are going to take that function space and we are going to make some operator operate on that function space. What is our goal? What is our goal? Why are we doing all this? To get an A at the end of the semester. What other than that? Yes? To get let us say, without being a spoil sport, let us say we want to develop a generalized method, right, of knowing how many reducible representations there are, what are their dimensionalities and what they are. Okay. That of course will come from great orthogonality theorem, yes, and they are interconvertible also. You take linear combinations, this plus 1, 0, minus 1 can become x, y, z. Similarly, you could have taken the 5 d orbitals. D orbitals is what is worked out in Bishop's book. I want to leave that for now because I want to handle d orbitals after mid-sem when we talk about inorganic complexes. D orbitals are also fascinating. Do you know why dz square orbital is called dz square orbital, or dxy is called dxy, or dyz is called dyz? There is a better way of putting it. Okay. So we will come to that. Just of course this question is like, when I was in school we had this O. Henry's story, I think everybody has read this. Some guy wanted to get into jail because it was winter, so he broke a window, the police did not catch him, he did a lot of things, finally he wanted to get reformed and he got caught. So that word cop was used there, and we had a question, why is a cop called a cop? Do you know why a cop is called a cop, by the way? It's actually a good question. Somebody wrote some other question, a cop because policemen used to wear copper helmets. It's cop from copper. That is why a cop is called a cop. So similarly, we will learn why dxy is called dxy, dz square is called dz square. We will also learn that dz square is only a nickname. Most of us have nicknames and good names, right? So dz square is not a good name. Dz square is only a nickname. We will learn what the good name is, but that is for another day. For now, what we are trying to do is, we have defined the basis. Now we want to define transformation operators, and today we will stop at just the definition. We will not go any further because then nothing will transform. Okay. So what we basically want to do is this, we want to write transformation operators for every symmetry operation, and this is what is going to happen when you make the operators operate. Over Fi in the transformed coordinate system, x1 dash, x2 dash, x3 dash is a transformed coordinate system. So the transformed function in the transformed coordinate system is going to be the same as the original function in the original coordinate system. Does that make sense? coordinate system, not base vectors. See, you move this point, so it has become something else. But now if you move the coordinate system along with it, same, exactly same transformation, then in the, so there can be two kinds of coordinate systems, right. One is the rotating, or let us not say rotating, molecule fixed or center of gravity fixed reference frame, the other is space fixed coordinate system. One can be absolute and the other can be along with the molecule. Of course, my left hand right hands will never meet again. So, you can transform the coordinates with respect to each other, right. So, what we are saying is that you studied NMR spectroscopy, right. In NMR spectroscopy, have you studied this rotating frame of reference? Rotating frame of reference? Let us take an even easier, simpler example. Have you seen record player? In ancient times, people used to listen to music from records which are like big, huge CDs, it's just that they are black, right. So, you see a record player, I mean the record is like a CD. So, when a record player is in action, what happens? You see that the record rotates, okay. Have you seen this movie Honey I Shrunk the Kids? Everybody has seen that movie. Suppose somebody shrunk you and you hopped on to the record, would you see it rotating anymore? Of course, the more tangible example is that do we feel that the earth is moving? We do not, because we are on the earth, but if we stand somewhere outside, then we will see the earth moving, right. So, that is the point. We do not perceive the change in earth because the earth is rotating, we are rotating along with it. So, the transformed us in the transformed earth coordinate, right, is the same as the original us in the original earth coordinate. That is all I am trying to say, okay. Does this make sense now? ORFI in the transformed coordinate system is the same as the original Fi in the original coordinate system. A, where is A? Fk, okay, Ik, these are just arbitrary letters, these are designators. Right now we are in this line, have you understood that line? Then we go to the next story. Next story is what we had written earlier, okay. Suppose you are working with a function space made of n linearly independent basis functions. Here I should have written Fk, actually I have written Fj and Fj, no, Fj is fine, for this Fj is fine. So, suppose you are working in a function space where you have n linearly independent basis functions, okay. You have already seen a relationship like this, right. We had written it earlier, E dashed. What is E dashed? E1 dashed. E1 dashed is nothing but OR E1, transformed basis vector. And here see, we are talking about linearly independent basis functions like your E1, E2, E3. So, we just write that earlier equation in a different form. On the left hand side we have OR Fk, where Fk is a particular function chosen from these n number of linearly independent basis functions. That clear? K is a particular function, maybe the 186th function, K equal to 186, let us say, okay. So, that OR Fk, that means the transformed coordinate, transformed kth coordinate will be sum over j, and here I have got it right, sum over j equal to 1 to n djkr. What is djkr? R corresponds to the symmetry operation. Djk is the jkth matrix element of the transformation matrix corresponding to R, and do not forget I write djk here because I have constructed the D matrix using transformation of the coordinates, not the basis, right, that multiplied by Fj summed over j equal to 1 to n. So, this is more or less what we had written earlier also when we had talked about that C3 operation example, right, is not it? here Ek dashed, instead of Ek dashed we are writing OR Fk, that is the only difference. When you make OR operate on Fk you get this, right, that equal to sum over j djk Ej. All we have done is that we have specified R a little in a little more explicit manner. Makes sense? I think we will stop here and we come back tomorrow and we start from here. What we will see is that these turn out to be what are called unitary operators, back to unitary, and then we will need to know two more things. What are equivalent representations, what are unitary representations. Once we have done this, then we are ready to derive what are called Schur's lemma. Schur is some European surname, Schur, Schur's lemma, and from there we are going to arrive at rate orthogonality theorem. So, I think by next Wednesday at least we should be there. If not on Tuesday, definitely on Wednesday we will have derived rate orthogonality theorem, and then in Friday's class what we do is, using rate orthogonality theorem we start deriving the character tables. After that let us see, I am in two minds. Either we will talk very quickly about vibration. I am a little reluctant to do that because it is discussed in CH442, or we will just get into what we did last year in this course, talk about what is called symmetry adapted linear combinations and discuss valence bond and molecular orbital theories. Okay. Please, I am going to send this right away, this presentation. Please go through it once before you come tomorrow. It is only tomorrow, right, not very far away. Please go through this so that we are ready to take this tomorrow. Thank you.